Okay, a task that I have not shown you how to do yet, or maybe some of you already do know how to accomplish this. Um, your calculators used to have functions in them that would do those conversions for you. I used to have a calculator that would change pressures, temperatures, and other calculations somewhere in the menu, and maybe they still are. I don't know where that would be, but that's perhaps not going to help you here. But changing Celsius to Fahrenheit, is that a simple task to do? You might not think so, but it actually is. Okay. So what conversions do we know from the Celsius scale, that a specific point that we know, whether it's melting or boiling on the Celsius scale for water? Okay, so what you need to do is pick one of those, okay? You want to talk about 0 or 100? Okay, so if we have 100 degrees centigrade, if we needed to change that to degrees Fahrenheit, we already know that it's this, okay? But that doesn't answer how you do every other scale or every other conversion, for instance. And it works the same or in a similar manner going from Fahrenheit back to Celsius. So this, we're just picking something that we know that usually at standard pressure, once water reaches 100 degrees centigrade, it should be 212 degrees Fahrenheit. Okay, so let's see if we can prove that. So in step 1, okay, you're going to take your initial temperature and you add 40 degrees, okay? All right. Then, in this case, once you get that answer, we're going to take 140, we're going to multiply that by 1.8. This is the key, depending upon whether you're going to Celsius or Fahrenheit. Sometimes you multiply, sometimes you divide, okay? So, if we take 140 times 1.8, that gives us 252. Then we take that number there, 252, and we're going to subtract 40. You can't just skip this step thinking, okay, we're just going to multiply this number by 1.8 and that's all we're going to do, because you added 40 on the first step and subtracted 40 on the last step. It doesn't work that way, okay? You have to do all three of these. So now, when you subtract 40 from that, what do we get? What a quinky-dink, right? And that's exactly what we would have predicted, okay? So it also goes for the same aspect if you're going from Fahrenheit to back to Celsius. So you can take a known value. So in this case, we can take freezing, okay? So if we've got 32 degrees Fahrenheit and we want to change that to Celsius, the process is still the same, but this is where it would be slightly different, okay? So in this first step, what are we going to do? Add what? We're going to add 40, okay? But if we have 32 degrees Fahrenheit, we know what should that be in degrees Celsius when water freezes? Should be 0. So let's see if that prediction would be correct. Okay, so 32 plus 40. Of course, I don't think we need a calculator for that, do we? Okay, then we're going to take this number, 72, instead of multiplying, we're going to divide by 1.8, okay? Chances are we should get 40, correct? In other words, 72 divided by 1.8. And holy cow, what a coinkydink, right? So then in our third step, just like what we had predicted, okay? You will always add 40 in your first step. Then I guess I don't know. It's kind of silly how I always remember this. What type of frequencies do you have for the radio? It's either what or what? FM and AM. So I always look at the second one. If it's Fahrenheit, I just think of FM. Okay? So that tells me in the second step, I've got to multiply. Okay? Then before you had playlists on your phone or shuffles or anything like that, and after cassette tapes, how would people listen to their favorite music? Compact discs. So then I just think of CDs here. So then this tells me in my second step, I'm not going to multiply, but rather what? I'm going to divide. So I always think of FM and CDs. Now whether that helps you or not, that I don't know. Okay. I think one aspect that you could probably utilize just logic is anytime you're going from Celsius to Fahrenheit, the number gets larger, correct? If you divide it, it's going to get smaller. So maybe just tell yourself, you have to multiply by that constant. It's always 1.8. So again, I don't know if that helps or not, but that's how you go from Celsius to Fahrenheit and Fahrenheit to Celsius. Okay? Then look at your paper, and if there's any confusion, we can try to point you into the right direction. World history. Anybody know their world history? Again, Krakatoa, I want to say, was maybe in the Pacific, somewhere in the 1800s. Okay? And then another one about 80 AD in Italy. Okay? Pompeii was that the name of the volcano? Then the mountain was called Mount Vesuvius, I think, as if my history is accurate. But anyway, a third one that you would not be aware of, but that did take place on U.S. soil. I don't know if your parents would possibly remember that, but and maybe they would. But that last one, okay. In 1980, the worst volcano eruption in recent history, and that actually occurred on U.S. soil, was in Washington State, okay? Not when we say Washington, D.C., although sometimes maybe we'd like to see that place go boom, but that's neither here nor there. Washington State at Mount St. Helens. At the time of the eruption, what was the pressure within the volcano when it erupted 1 week before the catastrophe? Is talking about what your initial conditions would be. Now, is this a scientific problem? Well, it probably is, but it might not be by the numbers that were given to you. So that's why you see such large numbers. You see that initial volume inside the volcano, 5.89. Print's getting a little small. Times 10 to the 11th liters. That's a pretty high pressure, as you can see, which you would be led to believe is probably accurate, because when that had erupted, typically these volcanoes, they go up and out. But here, I think just this entire side of the Mount St. Helens just collapsed going downwards. But still certainly a noteworthy eruption. There were 1,750 atmospheres and 550 degrees Kelvin. Okay? So then 1 day before the eruption, okay, the volume was 6.20 times 10 to the 14th liters. Why is that volume getting larger? It went from times 10 to the 11th times 10 to the 14th. Your temperature is going up. What else is going up? Pressure is. Now, you can't make that correlation like you can with Boyle's law and Charles's law, but in this case, it's 6.20 times 10 to the 14th liters. Is that volume 1 or volume 2? That is volume 2, okay? And a temperature of 4,117 degrees Fahrenheit. So the first thing that you need to do with 4,017 is add what number? 40. Then, okay, we're going from Fahrenheit to Celsius. You take that number, whatever 4,017 minus 40 is what, 3777? Oh, sorry, yes, 4,057. Yep. Okay, then you take that 4,057, you're going to multiply or divide by 1.8. You're going to divide that by 1.8, and then that number, you subtract 40. Now you've got it in centigrade. But then there's just one minute step after that. Add 273 to that number. Now you've got it in kelvins. Okay? So what it's asking, okay, at the time of eruption, not a week before, but at the time of eruption, you got these new set of conditions, okay? What was the pressure within the volcano? And of course, for those of you who maybe have this done, that pressure is a lot larger, which it should be. Because then, once that pressure is alleviated, okay, then that's where the mountain had collapsed. And we could get into more specific about eruptions when it comes to skin and infections, but sometimes that's cool, sometimes it's gross. For anyone who grew up on a farm or lives on a farm, I used to love doing this, okay? Cattle like to rub their necks on barbed wire. Don't know why, maybe it itches. But just like humans, and in bovine, you break that skin, it's now vulnerable to what? Infections. So it's not like little tiny infections that we see in our skin. We're talking about maybe abscesses about the size of this or bigger. So that's cool. You take a blade of some sort, you walk up to them, you stick it in there, pull it back out. Then if you really like watching it, you squeeze that, and then just let gravity do its job. Okay? Yeah, I think, yeah, for some people it's ugh. Okay? So, but sometimes maybe if you catch it just right, there's a little pressure inside that abscess too. So just like anything else, make sure you have your mouth shut when you're doing that. Because if you're standing there like this going, you might shoot that infection into your mouth. So, no, I'm not talking from experience. So, all right. Anything else? Oh, okay. It says, the normal respiratory rate for a human being is 15 breaths per minute. The average volume for each breath is 505 cubic centimeters, which is 505 milliliters at 20 degrees Celsius, so that would be 293 degrees Kelvin. And you're going to have to take 9,950, divide that by 1,000. So it would be 9.95 kilopascals. And you're going to take that 9.95 and divide that by what? How do you change kilopascals to atmospheres? Divide that by 101.325. So what volume of air at STP that an individual breathes in one day? You don't have to make that calculation times 15 times 24 hours. We're not looking for it. I don't know, I keep forgetting that. Well, you can. I think I've done that before too. But so to point you into the right direction, what's missing is we haven't talked a lot about STP yet. Okay? So before I forget, for those of you tuning in, disregard that. I want to keep that structure up for the first hour class so I don't forget to go over that. But what is perhaps a little confusing is you're looking for this variable, I believe. Temperature 2. What is standard temperature? Standard temperature in kelvins is what? Nope. It's 200 something. 273. And then what would the standard pressure be for STP? How many atmospheres? Just one. So you have your initial set of conditions. I believe you're looking for volume 2. And then here's your second set of conditions because it's talking about STP. All right? Okay. So the rest of the time is yours. We will do a slight review tomorrow. Problem quiz 1 over this chapter is on Wednesday. No class on Thursday because of conferences. It's a really short class anyway. And then perhaps a week from tomorrow, we'll be over in the lab to do an activity on Charles's gas law, and then we'll wrap this short chapter up probably a week from Thursday or Friday. So we'll catch up to you next time.